Hello. So in this video and the ones following, I thought we'd talk a little bit about planes. Now, planes are actually one of my favorite subjects in mathematics, especially where we're going with them. Up until this point, you've probably seen planes in only kind of a geometry setting. We've thought about planes as, that's a shape that intersects any 3 points. Well, when you choose 3 points, it intersects those points. It's defined by 3 points. Any 3 points in space will have some entity that intersects all of them, and that's what a plane is. So if we have 3 points, we can create a plane, and that's all great, right? That is a plane. But there's another way of thinking of planes, and what I'm planning to achieve in the next couple of videos is actually representing planes more algebraically, until eventually we actually have an equation, a standard equation for a plane. So how might we find the standard equation of a plane, right? It's not obvious at first, since we have all these different directions here. It's not as simple as a line, but maybe we could take some motivation from the line. So what's the standard equation of a line? Well, generally people think of ax plus by is equal to c, where a and b and c are just constants. This is just one way of writing it, but let's go with this for now. So what might the equation of a plane look like? Well, a line, when you have a line, that can only really go in 2 directions, right? I mean, it can only occupy 2 axes. You can have it in you can draw it in a 3-dimensional graph, but it's a 2-dimensional, it's a 1-dimensional surface, but it'll cross 2 dimensions, right? We're dealing with an x and a y no matter what. Even if you have it tilted in 3 dimensions, you can still create a plane that fully contains that line, and you're dealing with 2 dimensions. But with a plane, you're dealing with, you'll have to deal with 3 dimensions, generally, unless, it perfectly lines up with your axes. But maybe, since we tend to be dealing with another variable here, this plane will take on a form more like ax plus by plus cz equals d. Maybe it'll look like that, right? We don't know at this point. Who knows? Maybe it's not like that. Maybe it's slightly different. But that seems like a somewhat reasonable assumption, since, generally, a line can just be, x equals 3 or y equals 2 or whatever, and only deal with one variable, but generally deals with 2. And a plane will similarly generally deal with 3 variables. So maybe it'll look like that. But, at this point, again, we don't know. So how do we get to finding out what the standard equation of a plane is? And how do we need to look at this differently than we have so far? It turns out we need to look at vectors, because there's another neat way to define a plane. We can define a plane with a vector that is normal to it, and that means it's perpendicular to it. Now, to be perpendicular to a plane, that it seems kind of just clear what would be perpendicular to a plane, right? You have a surface and you have something perpendicular to it, and that can be a surface, however, like that. But, it's what that really means is that vector is normal to all of the lines, all of the vectors, all of the rays, whatever, in that plane, right? You can draw anything contained in that plane, and it's perpendicular to it. And that makes some sense that vector could define a plane, because if we just draw a vector, what's that perpendicular to? Well, it's perpendicular to this. Oh, and also this, if we rotate it, we can rotate it all the way around, and we're really just creating the surface here. And eventually we'll create just that, a surface, which is a plane that goes on to infinity. So when we have a vector, it defines a plane, just like 3 points do. Any vector defines its own plane. And if you have a plane, you can find the vector that defines it, but we're not quite there yet. So we have this, we're using this normal vector to define it, because this vector is perpendicular to the plane. And one more thing to point out before we go into the next video and we start looking at the math of this is very important. That's that the length of this vector doesn't matter, right? If this vector was a short little thing or a really long thing, or, wherever it's going, who really cares? It's still perpendicular to that plane. The length doesn't make any difference at all in defining a plane. The only thing that matters is the direction of that vector. So let's just recap what we have so far. If we have a vector, it's some position in space. Vectors don't carry a position with them, but let's give it a position in space, x, y, z. Then that creates a plane a plane that contains that point. That's a weird color I came up with. It's a very dull blue. It defines a plane that contains that point. And that's going to be very important to moving on when we're actually going to start to deal with things like determinants and cross products and dot products to define our plane algebraically. And I find this very neat, and I'm very excited to share it with you. Tune into the next video for more.